Good morning. The total 2 of you that are here. Everyone else, I guess, will tune in later. But man, how boring to watch a long video of just this. Anyways, maybe it doesn't matter. Maybe it's all the same. Okay, so just a reminder, right? So we don't have school on Monday, but we don't meet on Mondays, so it doesn't matter. But you have your test on Thursday, and we'll do a sort of a partly review, right? Go over some of the harder questions, but also I really want to show you guys how I want you to submit your test, right? So that we're ready for the test. And so we've got test number 1 on Thursday, which is October 15th, and review on Tuesday, right, October 13th, kind of less important. So we'll talk about how to submit the test, but also go through some of the harder problems. So definitely, I haven't made the practice test yet, but once you've gone through the practice test, or once I've posted it rather, I'll send out an email, and then I encourage you to have a look at it at least and see if there are any questions specifically that you want me to go through for the review, because that might be good if you've kind of seen some and said, oh, I need a little bit of guidance on these questions. So that's what's happening next week. So today we're going to finish the fundamentals. Fundamentals took forever. That's all right. It's kind of rude to call them fundamentals. It's a huge part of this course. And so they are fundamentals, but we'll be building on all these things throughout the course too. So just as a quick review, last day we talked about inequalities. And after inequalities, today we're going to talk about lines and graphing lines and kind of solving lines, if that makes sense. After inequalities, today is going to be a breeze, right? So we'll do another inequality to get started. But after that, it's just kind of easy, straight. Hopefully it'll be kind of familiar, y equals mx plus b type of stuff. So inequalities, we talked about linear inequalities, right? Where you have one value of x, or one power of x. And we also talked about nonlinear inequalities, which was that kind of bigger process where we had to factor and we had to find the solutions, and then we had to use a number line was the easiest way to do it, and figure out where the inequality was true. And then we also talked about absolute values. Absolute value inequalities, which were also a little bit tricky, but once you kind of dissolve the absolute value, then it became kind of a simpler linear inequality anyway. So what I said last day was try a 51 from 1.8. So from 1.8, number 51, said give it a go on your own, and then we'll use it as part of our review next day. And here we are. We're going to start with 51. So 51 had x plus 2 times x minus 1 times x minus 3 is less than or equal to 0. So here, one heads up is if we expanded this, right, our highest power of x would be 3, x to the power of 3, which we're not really having to deal with in this course. I've sort of promised that already. So but if it is factored like this, then we can easily go ahead and use those factors, and we can still solve this inequality. So remember, the steps were to move everything to, all the terms to one side of the inequality, so you're just left with 0 on the other side. That's the first step to solving these things. Then we would have to factor everything so it's as simple as it can be, right, on the term side, right? Now, it's already factored, and that's why we're able to jump in and do this one. Because here, right, x equals -2 and x equals 1 and x equals 3 are solutions, right? Are solutions, or I should say, oops, are the roots, right? We said the roots are where it crosses the x-axis, where it crosses the x-axis. Okay. So if we know that, then what we're doing here is we want to figure out, okay, where does this thing, so this, if we expanded it, we would see that it's this polynomial and it would have some graph. So where is this graph less than or equal to 0? So here, we want to find where the expression is negative. Right? Negative or equal to 0, which will bring in a kind of last ditch here. Okay. So we have the roots. Next thing we did, even though we were only dealing with 2 roots before, because we were only dealing with quadratics, right? Parabolas up or down. Now we have the roots. So what we did was we put these on a number line, right? And so here we had kind of a number line, and you don't need to space these out proportionately because then it can look a little wonky. You just want to have enough space so that you can look at this. So something like -2, 1, and 3. Makes sense that they're kind of equally spaced, but what I'm going to do is I'm going to put up little imaginary dividers here. Because what we said last day was, okay, this expression behaves the same for all values less than -2. And then it behaves the same for all values between -2 and 1. Same thing between 1 and 3, and then for all values larger than 3. So we just need to pick some value in here, and that's just to help us figure out if it's positive or negative, right? We're looking for, we want this thing to be negative, and so what we did was we kind of, we didn't solve this expression. Sometimes that'll get a little bit big and out of hand, but what we did was we plugged in some test value, and we figured out if it would give me a positive or a negative value. Okay. So what we did was we used this factored version, and we said, okay, if I've got x plus 2, and I'm going to write it pretty small because I want this replicated in each of these sections. So I'm just going to copy and paste this. Copy, paste, paste. Uh-oh. Need it to be smaller. Cheating, I know. There. Okay. Because what I need to do is I need to figure out what's the sign of this times this times this, right? And I just need to know how negatives behave, right? Even number of negatives is going to give me a positive, and an odd number of negatives is going to give me a negative result overall. So what I'm going to do is I'm going to just pick a test value here. I'll let x be -3, for example, just so I have something to think about. And it doesn't actually matter what value you pick. We're not going to solve for it anyways. Between -2 and 1 is my favorite, 0. Between 1 and 3, I'm going to do x equals 2, and anything greater than 3, I'll use 5, for example. Right? So just picking values arbitrarily somewhere in each of those regions. So now what I'm going to do is I'm going to work through each of these and figure out if they're positive or negative in this region. So I just do it by indicating if it's positive or negative. I don't actually solve it. So I do -3 plus 2 would give me a negative number. And you can try any value less than -2 would behave the same way. And that's why we're able to do it. -3 minus 1 gives me a negative value. And a -3 minus 3 gives me another negative value. So this, a negative times a negative times a negative, negative times a negative makes a positive, but then a positive times a negative makes a negative. So overall, this is a negative value. Same thing for the next one. Using 0 now, it's really easy to see that this is a positive. 0 minus 1 is a negative, 0 minus 3 is a negative. So overall, I get a positive times a negative makes a positive. And same thing for the next region, right? If x is positive 2, I get a positive 2 minus 1 is still positive, 2 minus 3 is negative. So I get this negative value. Same thing for the last one. If x is 5, I get a positive times a positive times a positive, which overall is, of course, a positive. So in terms of where is this thing negative, right? The region that we're looking for is here. So up until from -infinity to -2, and then between 1 and 3 is also where it's negative. Okay. We can imagine, so probable graph would look something like this. So if I use kind of my number line now, it should obviously be proportionate if I'm using it as a number line and a graph. But here, if I put x equals 0 here, oops, I need to extend it further. And using these cutoff points, -2, 1, and 3, what these results are saying, where it's negative, positive, what it's saying is, well, if it's negative up to -2, that means all the y's are going to be below the x-axis, which means it might look something like this, coming up from -infinity. And then it goes to positive between -2 and 1. So maybe some point here it switches over, because at 1 and 3, it switches to a negative. And then from 3 onwards, it goes to a positive result, right? So here, if we're looking for a negative result, then that's this region here, right? But also this region here. And then it's positive for the rest, right? So it's negative wherever it's below the x-axis, and so that's from -infinity to -2, and then from 1 to 3. Okay. One thing to keep in mind here is that we wanted it to be less than or equal to 0, and so it is including these endpoints because it can be equal to 0, which is what happens at each of these roots. And so the solution to this thing is from -infinity, being really careful to not put a square bracket around infinity. Infinity is not a number, it's an idea. right? And so infinity, you can't include infinity. So it's really important that you always put round brackets when you're dealing with positive or negative infinity. And so negative infinity up to -2, including -2. And then it takes a break, so we link them up with that little union U. And then it picks right back up from 1 to 3, including those endpoints, because it can equal 0. I said this was a probable graph, right? Because what I know is I know it crosses the x-axis at the roots, and I know where it's negative and I know where it's positive. But what I want to show you today is using Desmos just to check your work, make sure that everything is as you expect it to be, right? And so I can't remember if I've introduced you guys to Desmos yet, but Desmos is just an app. So use Desmos to check. So Desmos is just an online graphing tool, right? And you don't have to sign up or anything. You can just download it and it's free. And so, and it looks like, I don't have a pointer on the screen here, but it's at the bottom, that the green kind of graph looking thing. So that one. So this is Desmos. Now Desmos is really clever, and for the most part, you can plug in things exactly like you see them in the problem, and it'll show you the solution, or it'll show you the graph depending on what you ask for. So what I'm going to do is I'm just going to plug in the original equation that we were looking at. So using the brackets properly, x plus 2 and bracket times x minus 1 and bracket times x minus 3 and bracket. So it does look like what I suspected, right? And you can click the line and then see how it gives these little points. And if you click those points, it'll show you where those kind of important points are. We haven't talked about the maximum or the minimum, and we haven't really talked about the Y-intercept yet. Right? For now, we've only talked about the roots, right, where it crosses the x-axis. But so here, this looks a lot like what we developed, right? What we said. So it goes from negative to positive, and then it has to, at some point, it has to switch to kind of going up, 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 down, 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 and then it switches to a negative, and then at some point it changes course down here, right? Going down, 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 to going up, 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 and then it goes to a positive. So what you can do is you can hold your finger on the line, and it'll show you what the solution is at any point on the line. Right? Now, I want to try something because I haven't tried it before, because I saw that there's these inequalities down here. So I didn't try this with my last class, so we'll see how this goes. But if I put in the less than or equal to 0, it won't give me the line anymore. It should just give me the regions where this is true. Okay? So let's see here, less than or equal to 0, and it did, right? So now it's just showing, and you can zoom out here, but it's just going to be blocks where this is true. So it's highlighting that it looks like everything up to, hey, trying to click this here. Everything up to -2, it's not letting me click it, but that's okay. And then from 1 to 3 is also the solution. So you can check your work that way, especially if you're dealing with a big nasty one like we were just dealing with. So we'll come back and use Desmos later on today, but definitely check it out. Because you're going to be writing your tests at home, definitely it's good to know how to check your work, make sure that you're doing things right. All right. Okay. So that's the end of that from last day. And like I said, compared to inequalities last day, when we start doing lines today, you guys are going to be like, so am I missing something, or is it really this easy, or what? And that's okay. It's a nice way to end. And this little section here, little, it's huge, this huge section. Okay, so I'll keep an eye on the chat for any questions, but I haven't seen any, so you can just keep going. All right. So for a line, right, we first need to, so we're talking about straight lines. Straight lines, you might remember from probably high school or whatever, y equals mx plus b should probably ring a bell, right? Y equals mx plus b, even if you don't associate it with a line yet, right? After today, you'll definitely think, oh, okay, that's the equation of a straight line. There are a couple of different ways that we could write a straight line, but essentially if there's just an x, so no higher power than 1 on the x, you can usually rewrite things as a straight line. Or we've been calling them linear equations, right? Linear lines, linear equations are just lines. So a linear equation, right, or a straight line, will have a slope. Yeah? And the slope tells us two things, which tells us two things. First thing is whether this line is positive or if it's negative, right? So which direction is it going in? Whether it's positive or negative. So if it's positive, just looking in the first quadrant here, x, y, if it's positive, it'll look something like this, just kind of going up, 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 up. And then if it's negative is when it's kind of going down, down, down like this. Okay. So the sign of the slope tells us whether it's positive or negative. Right? And then the second thing it tells us is how steep the slope is, or how steep the line is, rather. So if you have a really steep line, then you might have something like this. Right here, the slope is large. Or you might have something like this, where the slope is small. Right? So depending on what the value of the slope is, it'll tell you how steep the line is. And the slope is that rise over run, which might trigger something from the past, right? Slope is rise over run. Usually we denote the slope with a lowercase m. And so we usually use m, so a lowercase m, to denote the slope. So what I'm going to do is I'm going to bring in, so from the notes, there. I'm going to bring this guy in. just so we have it for reference. So M, we said, is the rise over the run. And assuming that we have 2 points, so any 2 points, A and B, which we have the ordered pairs x1, y1, and x2, y2. Notice that we just use the subscripts to denote which point it came from. So all the subscript 1s came from A, and all of the subscript 2s came from B. Okay. What this is saying is that, okay, if you've got something like this, right, and here's your x and here's your y-axis. Sometimes I draw them. I should draw them. It's lazy not to, but sometimes I don't put the x and y on there. So if we've got a point A at x1, y1, and a point B at x2, y2, remember that x, y is an ordered pair, right? Just as a little side note, trying to think when we use them, but we have seen them before, but just as a refresher. So that's an ordered pair, and it's just a point on the coordinate system. So this here, this is at x1, and this is at y1, and this is at x2, and this is at y2. Right. So that's how we find those points. Now, if we need the slope between these 2 points, what this is saying is that we're going to take y2 minus y1. So that's this one, this y minus this y. And it doesn't matter which point is which, right? Because we're just using arbitrary values here. So it really doesn't matter which one is x1, y1, and which one is x2, y2, as long as you're consistent in treating the 2's together and the 1's together. Okay. So let's have a look at the rise. The rise is the distance from here, oops, that's a little crooked, here to here. So the rise is the distance between y2 and y1. So how we usually do that is y2 minus y1. The run is the distance between here and here. So the run is x2 minus x1. So if we have m, which is the slope, which is the rise over run, then what you have, and I'll use the same colors, y2 minus y1 over x2 minus x1. I'll use the neutral blue. Okay. So that's how you're going to find just the slope between 2 points. So let's have a look at some of these problems here. And we'll just pick one here. Let's do 12 together. So if you've got a slope or a point P and a point Q, pretty typical names for points, P and Q, doesn't matter. If P is negative 5, 1, that means X is at negative 5 and Y is at positive 1. And then Q is at 3, negative 2, so when X is 3 and Y is negative 2. We don't actually need to plot these, but it might be nice just to see, right? You could just say, okay, here are my subscript 1s, for example, and here are my subscript 2s. And then you can just go ahead and calculate and find the slope. But just for practice, let's plot these. Now I'm trying to remember if I can have, so a sticky, I want to have a grid. maybe I can use that. I don't know if it's going to work because I need to have, so it's good to be able to look at these if you're graphing them and to figure out what you need for your axes, right? So my x-axis goes from -5 to 3. So hopefully I've got enough room. -5, -4, -3, -2, -1, 0, 1, 2, 3. Hey, just about. I'm also going to make sure that I can go from y = 1 to y = -2. Looks like I have enough room here. So if I just put, I'm going to pick a point to have this at. I'm going to try -5, -4. Hopefully there's enough room. I can't remember. -2, -1. Putting this y-axis at x = 0. And then 1, 2, and flipped it. 1, 2, and 3. Yeah. There. Needed a slightly bigger grid, but we're gonna make it work. +1, 2, 3. -1, -2. Okay, so to plot these points, -5, 1 means that when x is -5, y is +1. Right? So what I'm going to do here is I'll put my point P, which is at -5, 1. And then my Q is when x is +3, y is -2. So that's down here. So Q is at 3, -2. Okay. I'm trying to find the slope between these two things. And like I said, we don't need to graph these. We're just graphing these and plotting the points for practice, right? Because we need to be able to plot points. But the slope between these two is going to be this minus this, or this minus this. It doesn't matter which order you do them in. So if we let this be x1, y1, and this be x2, y2, then the slope, which is going to be y2 minus y1 over x2 minus x1, is going to be, okay, y2 is -2 minus y1, which is 1, over x2, which is 3, minus x1, which is -5. Simplifying this, you get -2 minus 1 is -3. 3 minus -5 is 3 plus 5, which is 8. -3 over 8 is the slope. Or if P -5, 1 is x2, y2, right? So if we switch these, I just want to show you that you end up at the same thing. So it actually doesn't matter as long as you're consistent. And if Q is 3, -2 is x1, y1. Oops. Then the slope is going to be, okay, y2 minus y1 over x2 minus x1, which is going to be 1 minus -2 over x2, which is -5, minus 3. This becomes 1 minus -2 is 1 plus 2, which is 3. -5 minus 3 is -8. But whether the negative is on the top or on the bottom, you can just, there's just one negative, so it's just a negative value. It actually doesn't matter where this is, right? These are equivalent because -3/8 is the same thing as 3/8 because you can rewrite it as -3/8. Those are all different technically, right? But they all mean the same thing. Good. So there are kind of two, well, three ways, but we'll start with two. Two common ways that you can generate the equation of a line. So the most common way of writing the equation of a line is y equals mx plus b, right? Where m is the slope and b is the y-intercept, right? Where it crosses the y-axis. So what we call this is the slope-intercept form of a line. We call this the slope-intercept form of a line. And I'll go to the notes and pull out the little, I actually skipped the point slope form of a line just for a little bit longer because I want to show the slope-intercept form of a line first because it's the most familiar, hopefully, probably. So that's the slope-intercept form of a line. So when you have y equals mx plus b, then you can easily see that the slope is there, the intercept is b, whatever the constant is, and then that's easy enough. What we'll get to is we'll draw these lines, right? But for now, we'll just talk about the lines. The other way is to use the point slope form of a line. The slope-intercept form requires that we know the slope and the y-intercept, that we know the slope and the y-intercept of the line. Okay. The y-intercept is a specific point on the line, right? So the y-intercept is when x is 0, right? That's what puts us on the y-axis. Y is b if we're trying to match it, okay, equals b. Okay. This is just a specific point on the line. A specific point on the line. More generally, if we just have a point, so not just the specific point, but a point on the line, we can use the point slope form of the line instead. More generally, if we have a point on the line, so I'll put in brackets any point. So if we have a point on the line, any point, we can use the point slope form of the line. Point slope form of a line to generate the equation. So the point slope form of a line is the one I kind of skipped for a little bit. So this is just more general. Okay. And it just says that if you have a line that passes through any point x1, y1, and as long as you know the slope, so we still have to know the slope, but that's going to be the case for all of these lines. We have to know the slope. Or, right, what we saw earlier is if we know 2 points where this line goes through, then we're able to find the slope, and then that would be how we get the slope. But for now, right, we have to know the slope one way or another. And as long as we know 1 point that it passes through, we can rewrite this line as y minus y1, which is the y in the point that we know, which is m, which is the slope, times x minus x1, which is the x that we know from the point that we know. So y1 and x1 are both from the point that we know. Okay. Then, if we know these things, then we can just, we can solve for y and we can mold it into y equals mx plus b. But before we do that, I just want to go through an example. Let's do or should we practice our fractions, kick it up a notch? Yeah, maybe. Here, I'll zoom in a little bit. Let's do through the point 1,7 with a slope of 2/3. Okay. So for 27, our point is at 1,7 and the slope is 2/3. Okay. So we can use the point slope form of a line to generate this equation of the line. Okay. Knowing that x1 is 1 and y1 is 7. Right? So here, x1 is 1, y1 is 7. And of course, m is 2/3. But that one should be pretty obvious now. So we've got y minus y1 equals m times x minus x1. Okay. So now I'm going to go ahead and I'm going to plug in y1 equals 7 and x1 equals 1. Right? So I'm just going to plug these in, and I know my m is 2/3. Right? Just like in y equals mx plus b, there has to be just a plain y and a plain x. So you don't have to do anything. In fact, you shouldn't do anything with those. So what we do is we get y minus 7 is 2/3 times x minus 1. I'm going to solve for y, rearrange this thing, and see what happens. So I get y is 2/3 times x minus 1 plus 7, right? Because I had to move this 7 over to the right-hand side. So now I can expand this 2/3 inside the brackets because it's multiplying the brackets. And then I'll have the 7 that I need to simplify. 2/3x minus 2/3 times 1. I'm not going to write that, plus 7. Okay. This 7 looks so weird, but it's kind of cute, so I'll keep it. to simplify this, right, it makes sense because the slope is 2 over 3 and that's what's attached to the x, so that's fine. But I need to simplify this because that's just a constant, but I need a common denominator here. And so what I'm going to do is I'm going to multiply the 7 by 3 over 3 to get that common denominator. Because we've done so much work with fractions now that I expect you to be really good at them. And so now y equals 2 over 3x and minus 2 over 3 plus 21 over 3. So simplifying, I get 2 over 3x. Negative 2 plus 21 is plus 19 over 3, which cannot be simplified. And you can check that using your calculator if you've got kind of one like this. 19 divided by 3, helps if I turn it on. 19 divided by 3, it doesn't simplify. I don't know. See that? It's hard to see. But there we have it, right? So now we've got our equation of a line. Okay. We can go from the point slope form of a line to the slope-intercept form of a line, because like I said, the point that we know in the slope-intercept form is this very specific point of 0, b, right? So in this point slope form, if you let the point that you know be 0, b, let's see what happens. If we let the point that we know be 0, b, the y-intercept, in the point slope form of a line, we find that y minus y1 equals m times x minus x1. Well, now my y1 is b and my x1 is 0, right? And so I get y minus b is m times x minus 0. X minus 0 is just x. And so I have, and if I'm solving for y, I'm going to do it all in one go. Y equals mx plus b. So it ends up being the same. But like I said, this y equals mx plus b is just a specific case of the point slope form where the point that you know is the y-intercept. Okay. So there are some special lines, specifically a vertical line or a horizontal line. And so a vertical line, let's steal it here. So if we have a vertical line, then what that looks like is x equals a. So it actually doesn't care what y is because x will just always be a. And so what that looks like is if you have something that looks like this, and if you have x equals a here, then the line, a vertical line, is just something like this. Oops. Not very straight, is it? Try to start it closer. That's supposed to be straight, but the rest of my graph isn't straight, so, right? And so here, this is a vertical line. So try to make it a little bit thicker, there. And this point is at x equals a. A horizontal line is something that looks like this. So then it doesn't care what value of x you have, right? It's always just going to give y equals b. So if we've got our axes like this, and if I'm at a point y equals b here, then the horizontal line will look something like this. Easier because I've got the line. Right, so here, this is a horizontal line. I always have a hard time, or I used to have a hard time, remembering what's vertical and what's horizontal. But if you just think of the horizon goes like this, and so that's horizontal, and then the other one is vertical, of course. Some notes about the slope. The slope here, if you think about a horizontal line, the slope is rise over run, but there's no rise here. It's just going straight across. And so if you've got a 0 rise, 0 divided by anything is going to be 0, right? And so here, the slope of a horizontal line is 0. Now, a little bit trickier if we think about a vertical line, because now there's no run. X equals a, and that's it. So there's no wiggle room on this line. Now the run, if the run is 0, then we're dividing by 0, which is not allowed, right? So that's illegal math, so we're not allowed to do that. And so here, a vertical line, we actually say has no slope. Notice the difference in terminology, right? No slope is very different from a slope of 0, right? So just kind of keep that in mind, and as we get more familiar with lines and slopes and terminologies. Okay. Let's see here. So finally, I want to talk about the general equation of a line. So this is the one to look out for because anything with these 3 components would make a straight line, right? So we said, okay, if you have an x and the highest power of x is 1, almost said 0, 1. And then if you have a y in there, and you can have a coefficient on y, that's fine, and some sort of constant. And if you're able to move everything to the side and set it equal to 0, then you have a straight line, right? And so here, this is a linear equation, right? So if you've got an x and a y and that's it, and some sort of constant is allowed as well, and you're able to set it equal to 0, this is a straight line. So, but what you can notice is that we can solve for y in this equation, right? So if we solve for y in the general equation of a line, we find, okay, so I've got ax plus by plus c equals 0. Okay. If I'm solving for y, I want to get y on its own. So what I'm going to do is I'm going to subtract ax and subtract c. And so what I get is I get by is negative ax minus c. I'm going to keep the negatives here. I could pull out, I could factor out that common negative. I'm just going to leave it because it doesn't actually matter. And then I just have to divide by b on both sides. Negative ax minus c all divided by b. And the negative is only a. I can split this up, so I get y equals negative a over bx minus c over b. Here, notice that negative a over b is your slope, because it's what's attached to the x. and negative CB is your y-intercept, right? You do not need to memorize this at all, right? I'm just showing you that, well, we can rearrange this and we can have, like, we would have something kind of nasty here, right? And for the intercept, but we can still rearrange it into the form of y equals mx plus b, right? And so, so we can move from the general form to the slope-intercept form. All right, so we did a problem, I'm just trying to remember. Oh, okay, we did 27. So what I want to do next is I just want to get to graphing lines. So what's nice about lines is, because graphing them, if you think back to the example we started with, if you've got a non-linear equation, so powers of x that are more than 1, then you usually have some sort of curve, and it just looks kind of weird. But for straight lines, what's nice is you only need 2 points, so any 2 points on the line, and then you'll be able to connect those using a straight edge. So I usually use a straight edge like the side of my calculator or a piece of paper or something like that. And you can connect those 2 points and draw the line, and then you're done. So what's fun is to graph a straight line, oh, I've got a hair on my iPad, there we go. To graph a line, we only need 2 points. And they can be any 2 points. On the line. We draw the line going through these 2 points using a straight edge. We draw the line going through both points using a straight edge. I say straight edge because it doesn't have to be a ruler, although that's the nicest straight edge you have, right? But I used to, when I was in school, I used to keep just like a little business card that I would use as my straight edge. I usually had a ruler as well, but that's just extra. So, all right. So to graph a straight line, we only need 2 points. And so what we're able to do is, if I have the equation that I want to draw, then I can find points on this line. So first thing I'm going to do is I want to draw the graph of one of these. So what I'm going to do is let's do an easy one. Let's start with 57 first, and then maybe we'll do 62 after. So 57 has y equals 3 minus x. So it does say find the slope and the y-intercept, but we've been doing that, so I guess we can do it. The slope is -1, and the y-intercept is 3, right? Y equals mx plus b, right? You'd have to rearrange it potentially, unless you see it right away like that. So now, to graph, find 2 points on the line. to do that, what you're gonna do is just pick two values of x, any two values of x, and substitute them in here and solve for y. So pick any two values of x and solve for y. Because we're going to need x-y pairs. So what I usually do is I set it up like this. I have a little table, and because I need 2 points, I'm going to have x equals something and x equals something, and then up here I've got y equals 3 minus x. Usually what I'll do is I'll have a look at the equation that I'm dealing with, and I'll just pick nice values of x, right? So something that I can easily plug in here and solve for. So x equals 0 is a nice start, right? So if I let x be 0, then y is going to be 3 minus 0, which is 3. So the point, my first point as an ordered pair is at 0, 3. The second value, again, it does not matter what value of x I plug in here, right? It's all on the line, so it doesn't matter. I could put in 1.4 if I wanted to, but it's hard to graph, right? So how about we do x equals 4. Wow, crazy, right? 4, then y is 3 minus 4, which is negative 1. So the next point on the line here is at 4, negative 1. I'm going to use that sticky thing again, the stickies. Try a grid. I wish the grid was a little bit smaller, but that's okay. So now my 2 points that I have, and of course a line extends from negative infinity to positive infinity. So this line is going to keep going and going and going and going. So we're just zeroing in on these 2 points here, but the line keeps going. So if my x is 0, y is 3, so I need to have from 0 and then on the x-axis, and it also has to include 4. And then my y is from 3 to negative 1. So just kind of maybe putting it here. Sometimes you have to be more strategic than others on where you put your axes. So here I've got 1, 2, 3, 4, 5, 6. Negative 1, negative 2, negative 3. 1, 2, 3, 4. Negative 1, negative 2, negative 3. Okay. So my first point is when x is 0, y is 3. And if it helps, you can look here. When x is 0, y is 3. So I've got 0, 3. Right, that's my first point. My second point is when x is 4, y is negative 1. So my second point would be here. 4, negative 1. Okay. So now I can tell there's only one way that this line is going to go, right? It's going to connect this way. You can try to connect it some other way. I don't see it though. And so what I'm going to do is I'm just going to use the straight edge of my calculator here and just put it on both lines. And because I'm on my iPad here, might look a little bit different. But what I do is I just extend the line going through it. And now I've drawn the line. Just to start checking our work with Desmos again, let's just plug in this line and just make sure that it looks like what we just found. What was the line? Y equals 3 minus x. Oops. Y equals 3 minus x. Looks good, right? I found this point, and then if I follow along here, we could have solved for when y was 0 is when x is 3, and then we said when y is, or when x is 4, y is -1, and it's hard to get it to stop there, but it looks like we did it right. Nice. So let's also do 62 just for a little bit of an exercise in solving for y and that kind of thing. So 62. If you have 3x minus 4y equals 12, it's going to be easiest, especially when you go and you find your points. It's going to be easiest if you've already solved for y, especially because you're going to use it twice. So there's no sense in solving for y twice if you can just solve for it in general and then use it. It will be easier to find the points. If we solve for y first. So what I'm going to do is I'm going to have 3x minus 4y equals 12. And also, if we wanted to answer the actual question, which said, find the slope in the y-intercept, so that means solving for y. Y equals mx plus b is going to let us answer that question and then draw its graph. So we've got 3x minus 4y equals 12. So I'm solving for y, so I get -4y is 12 minus 3x. Y is 12 minus 3x divided by -4. Careful with that -4 because 12 divided by -4 is -3. Or I guess I could show it for a little bit longer. 12 over -4 minus 3x over -4. This negative and negative become positive, so we get y equals -3 plus 3 over 4x. So from here, right, we say that the slope is 3 over 4, and the y-intercept, which I'll just use a lowercase b, is -3. So now, if I'm going to graph this, I can graph this. This is equivalent to this. I've just moved things over. And so I need to find 2 points on the line. So I set up my table. 2, or if you want to be really careful, you can do 3 points. But what you'll find, especially if you've got a nice grid, is that they're all on the same line. So again, I'm going to pick a convenient value of x. So x equals 0, I think is really convenient still. There are situations where it's not that convenient, but usually it is. Y equals -3 plus 3 over 4x. So y equals -3 plus 3 over 4 times 0, which is just -3. So the point that we're plotting here, the point xy, is at 0, -3. Now, what I mean by convenient values of x definitely comes into play if you have a fraction, right? A fraction is a coefficient. Because now if I were to plug in x equals 1, then I have to deal with fractions, right? -3 plus 3 over 4, I'd have to get a common denominator here, and it just makes it really nasty. So what I'm going to do is I'm going to try to cancel with this 4. So any multiple of 4 is gonna work here. So now I'm going to pick 4, right? And I'll make a note here. Pick easy values of x. So we've got y equals -3 plus 3 over 4 times 4. Well, 3 over 4 times 4 is just 3. So then I have, let's cancel these. Boom, boom. -3 plus 3 is just conveniently 0. So the point that I'm looking for is at 4, 0. Checking in, if you have to draw your axes on your own, right, you've got 0, x going from 0 to 4, you have to have a room for at least those, and y is going from -3 to 0, so you have to have room for at least those. I'll use one of these stickies again. So if x has to go from 0 to 4, I don't really need negative x's. And if x has to go from -3 to 0, then I do need negative values of y. So I'm going to shift my y-axis around here a little bit. Y and x. 1, 2, 3, 4. 1, -1, -2, and -3. Good enough. So 0, -3, let's get it on here. 0, -3 is down here. And then 4, 0 is here. The x-intercept, we don't talk about the x-intercept as much, right? But it's just where it crosses the x-axis. Now I've got my points, and what I'm going to do is I'm going to connect these two using my straight edge here. Oh, there's a little bulge here, forgot about. Maybe I'll use a piece of paper for this long one here. Hopefully it works. Tough on the iPad, easy on paper. Ta-da. So you connect the points. Hey, that's really good. Got myself on the back. So now we've drawn this line, right? And again, you can use Desmos to make sure that what you did is right. But besides that, right, just knowing how to draw a straight line is really useful and really good to know. Okay, so let's talk about parallel and perpendicular lines. So parallel lines are when you have two lines that go like this. So just by looking at them, the definition of a parallel line makes sense. It just says that two non-vertical lines, so let's just copy this in here. Two non-vertical, so that means they cannot be like this, right? They have to be on some sort of slope. Two non-vertical lines are parallel if and only if they have the same slope, right? And so if you are able to show that two lines have the exact same slope, then you have two parallel lines. Okay? So that's that goes without saying, kind of, right? So if you have something like this, then you've got a line here and a line here. those are parallel lines. I'll try to make them parallel. More interesting are the perpendicular lines. So a perpendicular line, or two perpendicular lines, or when you have a scenario like this. So again, we're talking about perpendicular lines are like this, right? So not like this, but you've got a 90-degree angle or a right angle in here. And so if you've got one line that goes like this, then you've got another line that goes maybe like this, and then I'll show that it's a right angle, right? This is when they're perpendicular. So two lines with slope m1 and m2, again, we're just using the subscripts to denote, okay, here's slope 1, here's slope 2. They're perpendicular if we're able to show that m1 times m2 is -1. And then, or if it's easier, you can say, okay, well, you can solve for m2 here, right? If you just solve for m2, you get -1 divided by m1. And so these are equivalent, right? And you can use either of them to show that you have perpendicular lines. Another kind of caveat is if you have a horizontal line with a slope of 0, it will be perpendicular to a vertical line. But it doesn't really work out the same way, so that's why they had to add it as a little extra part. But I want to deal with things with actual slopes. But it's good to keep in mind that if you have a horizontal and a vertical line, they will be perpendicular. So let's do some of these problems. Let's do 73. Okay. So 73 says, okay, the equations of two lines are given. Determine whether the lines are parallel, perpendicular, or neither. So there will be scenarios where they're neither, and of course that just means that you've got maybe something like this or like this, right? And so more common is that they're not perpendicular or parallel. But if you have y equals 2x plus 3 and 2y minus 4x minus 5 equals 0, right? To save some room and some scrolling, I'm going to write them side by side because what I need to know the slope of this one. That's easy enough. It's 2, right? But here I'm going to need to solve this for y to figure out what my slope is easily. So here, m1, let's say, is 2. Notice that I'm just using the subscript 1. I'll use this as my first equation, this is my second equation. So now I'm going to solve this for y to see what my slope is. So I get 2y equals 4x plus 5. So y is 4x plus 5 divided by 2. So y is 4 divided by 2x plus 5 divided by 2. I guess y equals 2x plus 5 divided by 2, which means that m2 is also equal to 2. Right? So how I finish this is I argue with the definition, right? Two non-vertical lines are parallel if and only if they have the same slope. So we found that they have the same slope. So what I'm going to do is I'm going to say since m1 equals m2, and then to highlight that they both equal 2, I'm going to say equals 2. We know these lines are parallel. Or we can say these two lines are parallel. Okay. Let's try 75. only because I picked a bad one. I picked another parallel one last class. So now I know that 75 is not going to give me parallel. So I've got negative 3x plus 4y equals 4. And then I've got 4x plus 3y equals 5. So these are my two lines. Again, we're going to be really quick. I'm going to assume that you're really quick at solving for y here. It's not that big math. So 4y equals 4 plus 3x. So y equals 1 plus 3 over 4x. Do the same thing for the other side. 3y is 5 minus 4x. Y is 5 minus 4 over 4x over 3. So y is 5 over 3 minus 4 over 3x. So what I've found, right, is that m1 is 3 over 4. And here, m2 is negative 4 over 3. So you could look at these and say, okay, well, this looks like the negative reciprocal of this, right? If I flip it and then I take the negative, then that's what it would look like. For me, it's easier to just say, okay, well, if m1 times m2 equals negative 1, then I have proof that these two are perpendicular. So what I'm going to do is I'm going to say, since m1 times m2 is 3 over 4 times negative 4 over 3, and I'll just show here, 4 and 4 cancel, 3 and 3 cancel, so I'm left with negative 1. We know that these two lines are perpendicular. We know these two lines are perpendicular. Okay. So what I want to do now is I want to show you how to use Desmos just to check your work again, right? And so if we go into Desmos, and like I said, it's really clever, and you don't need to say y equals, but sometimes it's just nice to have the equations just as you see them on the page. So we're going to do that first one that we did, number 73, and just make sure that it gives parallel lines or what look like parallel lines. So the first equation was y equals 2x plus 3. Okay, so I've got a line that looks good. And then if I want to draw another line, then I hit this the enter button, the blue button in the very bottom right-hand corner, and it just gives me another line to put in an equation of a line. So I get 2y, and I'm just going to put it in just as I see it, minus 4x minus 5. And then I'm going to set it equal to 0, equals 0. So now I've got these two lines, and they sure do look perpendicular to me, or parallel, parallel, parallel. Okay. Let's try 74, just to see what it would look like, just so we know what to expect if we actually went through and did the work. So we have y equals, and then 1 divided by 2. Just be careful now. See how the cursor is by the 2? So if you kept typing, it would all be in the bottom. That's not what you want. So you want to kind of click it out, and you can just tap it. X plus 4. Okay, that's my first line. And then I have 2x plus 4y equals 1. So if I zoom out a little bit, they don't look parallel. It doesn't look perpendicular either. right? It looks like it's kind of off like this, and that's fine, so it's neither. So for practice, you could try that and make sure that you see that it doesn't, when you multiply the two slopes, it should not equal -1. And then let's do the one that we just did. So we have -3x plus 4y equals 4. That's our first line. And then we have, 4x plus 3y equals 5. So this looks a lot better. This looks like perpendicular lines. I don't want to mess it up again. Okay. So the next section, so that's Desmos to check your work there. The next section is kind of just to help you check your work, right? And so what we've been doing is we've been solving things algebraically, right? So algebraically is just when we do the math and we figure out what the answer is. If you're solving things graphically, then you'll be able to graph something and figure out where it crosses the x-axis, for example, right? And so thinking back to that first example that we did where we had that line that kind of snaked around through those 3 roots, that's what we did. We graphed it to see, just to double check that we had the right roots. But then we were also able to use it to figure out where things are negative, where things are positive. And so a lot of these, you'll be able to definitely, if you see this little symbol next to a problem set, then I definitely just want you to use Desmos, okay, or some sort of graphing calculator. If you have, you know, a TI-83 or whatever, that's good. But Desmos, it's free, so may as well use it, right? And so we're able to solve a lot of these, right? I say a lot because we haven't really been solving something with x to the power of 4 or x to the power of 5, right? But now, because we're able to graph them, we're still able to solve these things. So how about we do 14, right? And we can just solve it graphically. Okay. So here, let's just make a quick note. Section 1.11 is using Desmos to check your work. Sometimes we might be able to solve an equation graphically that is very difficult to solve algebraically. To solve an equation graphically, even if it is very difficult to solve algebraically. Right, so for example, which one was I? Oh yeah. Oh. For example, something like this, if you had to solve something like this, then that's pretty nasty, right? But if you graph it, so graph 2x to the 5 minus 243 equals 0 in Desmos. Actually, don't put the equals 0. You'll see why. We'll try both. We saw it in that first problem that we did, but So graph just the 2x to the 5 minus 243 in Desmos and see where it equals 0. Okay. So we've got 2x, let's get rid of those, 2x to the power of 5. Now, if you want a different power, there's a little a to the power of b button on the left-hand side. It's kind of hard to find, so 2x and then a to the power of b will bring the cursor up top there. So the power of 5, and then you want to step it down. Minus 243, oops, 243. Okay. Now, this is going to be some weird looking thing here. It's got a little squiggle there, so it isn't just a straight line, but if you zoom out, it ends up looking a lot like a straight line here. But what we want to know where this thing equals 0, right? So where does it equal 0? We can tap the line and we can see that at 2.612, the equation equals 0. And it looks like it only crosses the x-axis once. You can zoom out just to make sure, but it looks like it only crosses the x-axis once. We see it only crosses the x-axis once at now I can't remember what it was, 2.612, I want to say. It's an approximation, so that's fine. At 2.6120. So that's when it equals 0. And you can plug that in, right? You can say 2.612 to the power of, to the power of 5, to the power of 5 times 2, and then subtract 243. It doesn't get me to 0 because it's an approximation, right? Approximation, but it gets me really close, right? So it doesn't give me exact answers, but that's okay. So, let's see here. If I include the equals 0, how does it behave? So if I do equals 0, it just does a line. So that's not very useful. Where it becomes useful is if we have inequalities. So let's go to the inequalities, which is where we started today, actually, right? And so we can have inequalities like this. Oh, and I just had to put a little blurb on there. We can have inequalities like this, and we can figure out what the solutions are graphically. So if we do something like 33, and I'll leave the rest for you guys to do. 33, if we have x squared is less than or equal to 3x plus 10, what I want to do is, in order to graph these things, just like when we were solving them, I want to get all my terms on one side and 0 on the other side, because it's always going to be easiest to kind of look at things, where is it 0, where is it not 0. So I get x squared minus 3x minus 10 is less than or equal to 0. Right? If I've subtracted everything away from the right-hand side, I'm left with 0 there. So if I graph this, right, it'll show me the actual graph, and we can use that to see where is it less than or equal to 0. If I put this whole thing in Desmos, it'll show me the regions of the solutions. Putting this whole thing in Desmos shows the regions potentially of the solution, right? To see the line or to see the curve, because it's x to the power of 2, so I know it's going to have some sort of squiggle. To see the curve, only put x squared minus 3x minus 10 into Desmos. Okay. So let's see what those look like. And we're going to have the same thing like when we started today. So I've got x squared minus 3x minus 10. Now I have to zoom out a little bit here. Right, it looks like this, and if I click on my line, I can see where it crosses the x-axis. So what we wanted to find was where this thing was less than or equal to 0. So it looks to me like all of it is just less than or equal to 0 here. Between -2, so x -2, these are all negative results until I hit 5 again. Okay. And then it's positive. So now, if I put that whole thing in there again, so x squared minus 3x minus 10, minus 10, so now I've got that exact same line, but now I'm going to use those inequality symbols, less than or equal to 0, right? It just shows where the solutions are. Okay, so this I'll just highlight is between -2 and 5. So what I'm going to do is I'm just going to, here at -2 and 5, right, we saw that it looks something like this. So this is the region where it's negative. Okay. And then what it showed is that, okay, well, from here to here, this is the solution. Okay. Before I let you guys go, I just want to take you to Moodle just quickly and show you, make me log in again. Maybe, yeah. So, I posted all the solutions to, so you've had the 1.3 solutions, that's in week 3, but then what I did was I posted all the solutions as well as problems from section 1.1 and 1.2 because we didn't have them incorporated in the notes, as well as solutions at the end. So you have all the solutions to all the, I guess it rearranged my order, but that's okay, you'll find stuff. And so have a look at those. Even though I don't have a practice test ready for you guys quite yet, I'll email you guys when it's ready. But just go through the sections and just pick random problems, and then you've got the solutions so you can check your work. And I think that's going to be your best study tool, is just focusing on these problems that I've given you already, and making sure that you've got all these concepts. So I haven't seen any questions. That's the end of the fundamentals. But like someone commented in the class before this one, the fundamentals took a long time. And they do. They take a long time. It's a lot of the course. So that's why I think it's kind of rude to call them fundamentals. But anyways. Any questions, you three?
We'll get a review on Tuesday, right, for the test?
Yeah, exactly. So I'll make sure that everyone knows how to do that, like how I want you to do the test. how do you submit it, how do you get grades, that kind of stuff. And then we'll work through some practice problems as well. Any other questions?
Thank you.
All right. Have a good Thanksgiving, you guys.
You as well. Thank you.
Thank you. Bye, guys.